Let's assume that we have a finite sample space. So omega is finite, and let's say it has size n. We can always put the uniform distribution on omega, specifically saying that we pick p of little omega to be the same for all little omega, basically a constant function. Now it's pretty easy to see, since there's n points and they all have the same value and they add up to 1, the value has to be 1 over n. So p of little omega is 1 over n for any point little omega in big omega. Moreover, the probability of any event is just the size of the event divided by n, just the number of elements in it. So computing probabilities basically boils down to counting in a lot of cases. So what we're going to see going forward is that often combinatorial expressions show up, and that should not be surprising. Okay, let's consider a concrete example. Let's flip 4 coins, assume that the coins are fair and independent, meaning that the probability of heads and tails are both a half, and each flip is independent of the others. Let's let x be the number of heads. What's the distribution of the x? Specifically, what is the probability distribution of this random variable? Well, if you look here, we could just list all possible 16 things that could happen. It's a sequence of 4 symbols, either of which can be an H or a T, so there's going to be 16 of them. And we go through and we count how many heads are in each of these lists. And when we tally these, we get the pattern 1, 4, 6, 4, 1, which should not be surprising because we're just asking, given a sequence of 4 things, what's the probability that we have 4 or 3 or 2 or whatever in some set? Converting this to probabilities and knowing that the sample size is 1/16, what we get is we can compute the probabilities of any of these possibilities from heads. And notice this just comes from Pascal's triangle, right? So these coefficients 1, 4, 6, 4, 1 are just the coefficients in the 4th row of Pascal's triangle. We divide by 2 to the 4 because those all sum up to 2 to the 4. In general, if we flip n coins and we want to ask what's the probability of k heads, we should get a formula that looks something like n choose k times 1/2 to the n. Let's generalize this idea a little bit. Let's consider the following scenario where we perform n experiments in a row, assume that they're independent, assume that the probability of a quote-unquote success is p, the probability of a failure is q, which is 1 minus p. We then ask, what is the probability of k successes? We're going to denote by the following notation. So bin NP, bin is short for binomial, so this is the binomial random variable. This is going to be the random number of successes. And here's the theorem that we're going to prove. The probability that the binomial random variable is equal to k is n choose k times p to the k times q to the n minus k. Let's repeat that formula. Note we have a small typo there that we're going to fix in a moment. And let's prove this. So let's consider one concrete example. Let's imagine the sequence success, success, failure, success, failure, in that order, okay? So the probability of successes is p, the probability of failures is q, and since these are independent, the probability of this sequence is just the product of those 5 numbers, which is p cubed, q squared, and it just counts the number of successes. P cubed, the 3 comes from 3 successes, q squared comes from 2 failures. Notice that any sequence with k successes and thus n minus k failures is going to have probability p to the k times q to the n minus k. This is the probability of any particular sequence. But notice there are n choose k such sequences. Therefore, the total probability of seeing k successes is n choose k times p to the k times q to the n minus k. And we're done. Okay, quick sanity check. Is this thing a random variable? Does the probability distribution actually add up to 1? That's the thing to check. Well, let's go ahead and check it. If we add up k equals 0 to n of these probabilities, well, after a little bit of algebra, we just use the binomial theorem and see this is p plus q to the n, and p plus q is 1. So yes, it's 1. Note, to recover the case of the fair coin, in that case, p equals q equals 1/2, so we get the formula we had from before. All right, let's do a quick calculation. Let's say we flip 1,000 fair coins. What is the probability of exactly 500 heads? That's the number we kind of expect, and it's not so hard to see that that's the most likely outcome. But how likely is it? It turns out that it's about 2.5%, not very high. The exact formula is exactly 1,000 choose 500 divided by 2 to the 1,000. But it's really hard to get a sense of how big that number is because we have a huge numerator and a huge denominator. So what is the quotient? Is it close to 1 or close to 0? So we have to do some asymptotic analysis to get a sense of how big this number is. Okay, to attack this, we need a special formula that's called Stirling's formula. Now I'm going to write it down, and for now, just trust me. This actually is true. It says that n factorial is approximately equal to the following complicated thing on the right-hand side, which is n over e all raised to the nth power times the square root of 2 pi n. Let's just go ahead as if that formula was correct. So we want to compute 2 to the n choose n times 2 to the minus 2n, or alternatively 1/2 to the 2n. Where does that come from? Remember, we're asking for the probability of getting exactly half of a set of coins heads and the other half tails. So of course the only way that can happen is if the total number of flips is even. So here we're using n to be the number of heads, 2n the total number of flips. Let's crank out this formula. So we know that that is 2n factorial over n factorial from the formula for the combinatorial coefficient. So when we expand this using Stirling's formula, we do some algebra. And what's kind of amazing is that almost everything cancels except this little square root term. And what we get is that for large n, 2 to the n choose n, divided by 2 to the 2n is approximately 1 over the square root of pi n. It's kind of amazing. So what does that mean? In particular, that means as n goes to infinity, the probability of getting exactly half heads does go to 0, but it actually doesn't go to 0 that fast. It goes to 0 like 1 over a square root. Not super fast. In any case, just to check, when I choose n equals 500, which was the original problem we talked about, we can compute the Stirling approximation, and that gives us 0.025231. The actual answer is 0.025225, so it's a pretty good approximation. I'll stop there.